Okay, so the scope of today's lecture will be uh, learning about Monte Carlo method for determination of the units, the value, exact value of pi, and what is its application in astronomy. And afterwards, we will be dealing with optical image processing of a real astronomical data set from Liquid Mirror Telescope, International Liquid Mirror Telescope, situated at Aries, which is a 1.4 meter liquid mercury telescope, which is used as a reflector for the primary mirror of the telescope. The telescope is actually a collaboration between Indian science organization and Belgium, and so we have got a very new data set from one of my colleagues from Aries. So we will be using that data set. It's actually the data set from of a supernova which happened in 2023. So so this is very recent data set. So we will be doing some processing with it, and we will be learning about what are biases, what are flats, and how we normalize the flats, and how we extract a good image, clean image actually. So the images you see from the Hubble Space Telescope and other telescope that are viral on social media is not actually what a telescope captured. A telescope capture a very raw image that looks very noisy. So we will be looking after that. So first topic is our. So this was actually not in our syllabus of. Our AGN school, so they actually provided me the here the data. So I thought that it will be very beneficial to share with you guys as well, so that you can also learn how to do the processing from the real image of the telescopes. So it will be very beneficial, but for a while right now we'll stick to our syllabus, which is our today's topic, that is statistical methods, that is Monte Carlo method. So Monte Carlo method. So basically, Monte Carlo method is a numerical technique that solves mathematical or physical problems using random sampling. Instead of solving an equation analytically, we generate many random points and use the statistical methods to estimate the answer or the perfect numerical unit for that. So in astronomy, there are wide uses of Monte Carlo method, like galaxy formation simulations, estimating uncertainties in measurement, or orbit determination for asteroids and exoplanets, or even in star cluster studies. And also in mathematics, there is a very famous example, which is estimating the value of pi using the Monte Carlo method. So first of all, I will be writing some formulas, some basic concepts here. So I'll just choose okay, so the glitch happened. I'll just refresh this page. Yeah, so I'll just write Monte Carlo again, Monte Carlo method, and I'll convert this into markdown, and I'll convert the second one into a raw, where I will write the concept of the Monte Carlo. So imagine a square of side length 2 with a circle of radius 1 inside it. Okay, so you have a square inside which you have a circle. So I'll just write the theory here. Imagine a square with side length 2 with a circle of radius 1 inside it. So we know equation for circle is x square plus y square is equals to 1. uh, okay, if it's not shifted and the origin is at 0 comma 0. So this is the equation for that type of circle. So we are considering that its origin is 0 comma 0. Okay, so we know area of the circle. So this is actually for calculation for estimating the value of phi. So first of all, I will just write here heading application to cal calculate the value of pi. Okay, so yeah, now area of the circle, pi r square, right? uh, Now let's say for the square, what is the area? Area of the square will be 4, right? 2 cross 2, right? 2 multiplied by 2, 4, because we have assumed the length of the square 2. So you can assume it double, but nothing will happen. So it's depend upon you what you take, right? So now if we have a ratio of both area, sorry, area of circle and divided by area of square, it will be pi by 4, right? Because area of circle will become only pi, because r value is 1, right? So it will be pi by 4, the ratio. So if we throw a random points into that square, so point inside the circle will satisfy x square plus y square less than equal to 1. Point outside does not satisfy this equation, right? So I'll explain you with some visual. So then the pi value will be approximately 4 times of point inside the circle divided by the total points. Okay, so this is the formula for estimation. So let's assume you have a tiffin, a square tiffin, lunch box, and in the lunch box you have a circular bread or chapati. So you have a circular bread inside it, and now in the circular bread, and you want to just calculate the value of pi for that circle. So uh, the circumference of a circle is 2 pi r, and if we divide it by 2 pi, 2r, it will actually give us, if we divide it by the diameter, right, it will what will be it will be giving the value of pi. So when we are dropping some kind of chili flakes, let's say, onto that lunch box, you will see that some of the chili flakes, or let's say, let's assume you have a pizza inside it, okay, pizza inside the lunch box, and it's actually exactly fitting inside the lunch box. Okay, so now you are sprinkling the chili flakes or oregano, whatever, onto that square lunch box, and some of the chili flakes are getting on to that pizza, and other are getting out of that pizza into the rest of the portion of the square. So now the points which will get inside the circle, let's say we have around 10 lakhs, or let's say 1 million chili flakes, and it cover the whole pizza, and it gives the shape of that pizza. If we get the uh, chili flakes that much, which actually give the shape of the pizza, and we remove that pizza out of there, and just we have a circular chili flakes portion, then we can actually find out the value of pi by just giving it a random sampling. But the sample size must be larger. If we just have 10 particles of 10 chili flakes of that thing, then we are probability of getting those chili flakes onto that pizza portion will be very less. So more will be the chili flakes, more will be the random sampling, more accurate will be the value of pi. Okay, so what is the condition? If we throw the points into the square, then number one, the points inside will inside the circle will satisfy x square plus y square less than equal to 1, right? So also, of course, points outside the circle will not satisfy this condition. Now, then what? Then pi will be is equals to 4 times, oh, 4 times point inside the circle divided by total points, that is the sample size. Okay, so this is the concept of calculating the value of pi. Okay, so you just need to implement in this Python. So how will you do that? What we will be what will be required for this process? So the required packages will be of course numpy, because we will be using some random sampling. So I will write import numpy as np, and let's say that our sample size n is equals to, let's say, 1 million. Okay, so let's say 100,000. Okay, now let's say x is equals to np dot random. So these are actually generate random x and y coordinates, so you know, right? Random dot uniform, so it will create a uniformity -1 to 1 and n values. So -1 to 1 is actually we are defining the radius of the circle, so we will be applying the basically equation of the circle, so that it extends from -1 to 1, so that it satisfies the equation x square plus y square is equal to 1. So similarly for y itself, np dot random dot uniform -1 to 1 and n, and so the inside point will be x square plus y squared is less than equal to 1. Now estimating pi value, so pi will be is equals to pi estimate will be equal to 4 times np dot sum. So summation can be used like this. Also you can use some add, but right now we have a lot of values, so we will use summation from numpy. So it will be like inside values, so it will be like doing the summation of all inside values divided by total sample size. So now let's say print. Now we will be going to print the values for these things, estimated as well the real values. Okay, so what we are going to do is estimated pi is equals to, okay, so it is equals to pi underscore estimate, and similarly actual pi is equals to np dot pi. So when I'll run this program, you see estimated pi is 3.13 and our actual value is 3.14. so you see how close it is. So this is the method when we don't know the actual value of pi, but we know the concept how to calculate the actual value of pi. Okay, so this is actually used for random sampling. Okay, so it is actually used many times in the simulations when we don't know the actual values, but we can do a random guesses. So we are applying some random Monte Carlo method. Now let's make a graph of it to see how it fluctuates. Okay, how the value fluctuates. Now what I will do is, just a second guys, just a second. Yes, so now we will be making the image of the tiffin. Okay, so we have these x and y here already, so we will be making a circle. So we will be defining a theta. Theta is equals to np dot length space, and it will extend from 0 to 5 times np dot pi in 2000 distributions, and radius is equals to 1, and let's say a is equals to radius dot np dot cos theta, and similarly b np dot sine theta. So you know this actually give us the equation for circle. So we can present any point on the circle using using director circle and all those methods, parametric equation of the circles. So these are some type of the journal equation in the form of a theta value. So plt I'll give a space here, plt dot figure, and fig size is equals to let's say 6 comma 6, because we need a square image, this that will give us a better visualization. And scatter will be actually those points we are actually putting inside the throwing inside the tiffin, so which is x and y, x comma y, and let's say alpha is equals to 0.5. So basically it refer to the opacity of that circles. Okay, so this will be some kind of transparent. Okay, now plt dot plot a comma b with line width is equals to 3, and color is equals to red. So r refers to red also. So you must be intelligent enough to understand. I am using shortcuts now. Okay, lw color, earlier we were using red and line width as a full, so you can also use like this. So integer object, so it gives some error here. It says integer object has no attribute np. Oh sorry, we have to multiply the radius. Sorry. So it is r cos theta r sin theta, right? B in the equation. So it will be something like r cos theta and r sin theta. So when I will do that, plt is not defined. So yeah, this is our mistake. I'll write here only import matplotlib dot pyplot as plt. So you see here alpha, sorry, spelling of alpha is wrong. Okay, now you see our sample size were too large, so you see it covered whole of the tiffin. Now I'll decrease the sample size to let's say 1000. Our actual value of pi actually fluctuated, so you see here, right? So now the sample size was less, so many of the places are blank now. Okay, there is no chili flakes at that place, and some of the outer places are also blank. So more is the sample size, more it will fit inside the square, inside the circle, and it will give more shape and accuracy for the value of pi. So okay, so this is the thing here. So when you will decrease the sample size, it actually decrease the value accuracy. So more will be the value, more of the random sample size, it will be giving you the more accuracy. But I'll give you the question here that please don't increase the sample size a lot, otherwise you will be getting some heat issues if you just give it like 0.0000 a lot times. So because it is actually computational heavy thing, so it is not a nested kind of thing, so it goes from 1 and this 1 2 3 4 5 points like this, so it take times to process. So now what we are trying to do is we will be creating a plot of how values are fluctuating. Let's say when the sample size is 1, when the first point is thrown on the table, what was the sample size, what was the value of pi, and when the 10,000 were thrown, the last one was thrown, what was then estimated value of pi. Okay, so what I will do is now I'll create a here, let's say the starting points are circle points, on starting is 0, square points. So we will be applying loops, right? Remember, in the while loops and the for loops, we've earlier actually we earlier defined some initial values to them. Okay, similarly we are defining that initial circle and points inside when there is no point is 0, and value of pi is some list which will be estimated, so it's a null list for now, so value of pi also start from 0. So for I in original distance, so we will be defining original distance here, original dist, and if I is less than equal to 1, circle underscore point underscore points will be plus is equal to 1, so the circle points will increase. So what is the so let me tell you, first we will define the original distance. So original distance is actually I'll just show you once. Just a second. It's actually, guys, this thing, this formula only. So what we have done is we have given it that if the value of this formula is less than equal to 1, it will be giving the circle points. So I'll just firstly define or distance. Or distance is actually the radius of the circle. So if the radius of the circle and the points are inside the that radius, it will be giving us that thing. Okay, so x multiply by 2 plus y multiply by power 2. Okay, so plus, so it's actually kind of that thing. So okay, so now coming back to our loop. So first we have applied a condition here inside the loop. Now I will be making a second thing for the square. Otherwise, okay, so if this is true, then this then we can't we can use else also, but here no need because we already have a loop here, so you can also ignore that thing. So which will be 1, and so basically temp is actually estimated values, you can say est, or so estimated value will be 4 times circle points divided by square points. Just a second. So why square points, why not the total points? Because square points are also the total points, right? So it cover whole of the circle as well as square. So yeah, so pi dot append est, append means it will actually summation whole of the values. Okay, so it will it will actually not summation, it will actually add pi as the value estimated. So if the value is like 3.14, it will fill the null list as 3.14 as its first value. Okay, so if it has some other value, so it will update that pi list. Okay, so pi is equals to np dot array pi. So what I have done is I have made the new value of pi, that it will not no more will be the list, it will be the arrays. Now let's say x is also blank here. So for I, so x is actually our the sample size. Okay, so I in range, what was the sample size? 1000, right? Earlier it was 1000, so make sure it remains 1000, because you have defined the x and y value based upon n. So if the n is not 1000, so you have to change the value of here, because otherwise it will give the error that the sample size and the value of x is not same. So we will append the I values in this unit, in this list for x values. And now what I will do is plt dot x label, in the x label I will write number of points. Okay, and plt dot y label I'll write estimated pi value. So till then I recommend you to download the ILMT dataset, because we are already almost done with the statistical analysis of Monte Carlo. So then we will be doing something very crazy. Okay, so plt dot plot capital X and pi values, and plt dot show. So you see here how much it's fluctuating, how much at from 0 to 10 we have so much fluctuation. It started from 4, then come to 3.6, and then again increased, and then again increased, and then it come lower and lower and lower, near to the value of 3.1 approx. Okay, so which was actually, what was the estimated value? 3.116. so it is around 3.116. so make sure the value in the range value of the x will be the same as n. If I increase this to 10,000, I'll get the error. What will be the error? That x and y must have same dimensions. So earlier it was 1000, so it must remain 1000. So this is how it fluctuates. Okay, so now this is all the statistical stuff. You can also do that in 3D if you want. That will be giving the same thing. So using a sphere. Okay, for that you have to apply the equation for sphere. So that's your homework. If you want to do that out of your curiosity or out of this thing, you can work on that. Now we will be shifting to something very crazy. So what I will do is I'll come back here and I'll edit the name of this file, and I'll write day 5 Monte Carlo. Okay, now I'll just save this page and come back. Now I'll create a new clean notebook, which will be again day underscore 5 underscore ILMT. So I'll just want to show ILMT telescope to you. ILMT telescope. On the first link it's very there. So this is actually the telescope, ILMT telescope. I'll just go to Aries site itself to show you the exact image. So this is actually the telescope. Oh, what's happening? So yeah, so this is actually the telescope. It's inside this building. So it is actually located at Devasthal Observatory, and it was actually the first light was taken in 2022, and luckily in 2023 it captured the supernova as well. So you see here it is a liquid mirror telescope. So it has a thin mercury mirror, which actually uh, give it a proper shape. So why the mercury mirror is used? So it actually give it a flexibility, so it can change the composition of the image, the reflectiveness of the image, so the mirror, so that it can get more efficient to capture that light. So that's why this is the first liquid mirror telescope of India. So this is situated in Aries now. So yeah, so you can see here it is a 4-meter diameter telescope with aperture f2 f by 2, f ratio is 2, and it's again using the same filters that SDSS uses, uh, and covers the optical range, I guess. So these are some of the technically information you can just read on the official Aries Aryabhatta Research Institute of Observational Sciences page, which is stand for Aries. So yeah, so you can just go and check this thing here. So now let's get back to something really crazy. So first we will be importing all our uh, things. So first we will be going to download the things. So processing ILMT raw data 2023. Okay, now let me make this more cleaner. Now first we will be installing some libraries. Pip install ccd proc, pip install sorry astro query. Okay, so astro query will not be used right now, but you can just download it prior, because we will be using it in our tomorrow's session. Okay, so so I want you guys to attend the lectures now. You might you may have missed the earlier session, it was okay, but missing these session will make you go slow. Okay, so these are very crazy lectures upcoming. So we will be dealing with the actual dataset and processing them. Okay, so I'll just press enter. So okay, install. So require it's actually already installed for me. So what I will do is I'll make it as raw, so you can just download that from here. From astropy I'll import all these things. .io import fits. From astropy dot stats, this is the new thing we will be going to work. Import sigma underscore clipped underscore stats. So this is very useful, I will be showing you why. Okay, so from astropy dot and data import nd data, nd data. Okay, import ccd data. Okay, now from astropy import units as u. Also from numpy, import numpy as np, import mat plot lib dot pyplot as plt. Okay, so it will take some time. So yeah, it runs successfully. Now I want to open some of these fits file. So if you have already downloaded these fits file, you will see a folder which contain all of these fits file, right? So these are actually some of the sample uh, IPython notebook. You can check afterwards. It was actually given by my friend to me, my colleague to me. So you can actually do the same thing. So we will be doing one of these processing today. So you can also open these as for reference if you want, but if you want to continue from here, you can definitely. Okay, now uh, if you open this folder, this fits file, which is named as SN 2026 IZF X, okay, underscore I underscore 01 underscore 02. When you will open this, it will open in DS9. Hopefully you have not deleted the DS9, and you see this is a blank image, right? Now I will go to scales and I'll press log or histogram. Okay, so what I will do is I go to the histogram and try to just drag my mouse from right to left, and you see the textures will change. And when I'll drag my mouse upside and downside, it will change the contrast. So I think uh, this will be fine. Okay, so you see there is a galaxy, and actually the supernova is somewhere here. Okay, so you see on my top right, there is one zoom in image and one whole image. So supernova is actually somewhere here. So now what we'll be going to do is we will be trying to first of all the process the images, and we will be learning about the concept of bias frames and the flat frames, and then we will be definitely using astrometry to calculate the exact positioning of the stars inside these pixels actually, because we right now have the pixel values of the stars, but we don't have the RA and declination of those stars. So we will be also using astrometry. So for that purpose we will need some APIs. So I'll show you how to fetch those APIs. Okay, so this is how the image look like, but it has noises, it has some patches here. You see this patch, it might be some instrumental patch or something dust on the telescope. So we will be removing that. We will be processing all of the image here. So first of all we have to import the bias frames. So I'll show you one of the bias frame. I have shared you the data here. So when you will open this bias underscore 0. Uh, bias underscore 1, so you see here, I'll just open this again for you guys. So you see it is just like a old television noise. Okay, so what is a bias frame? So bias frame is actually used to cancel out the noise that is taken using the telescope, that is unnecessary in the image actually. So now bias frame is taken when the shutter of the CCD camera is actually covered. So there is no light of the from the sky, so there will be some uh, zero shutter value. So at the zero shutter speed and negligible shutter speed and zero exposure, so it will capture a blank image. Okay, so it will capture a dark image. So the expected value of the pixels must be zero, because it will be just a dark image covered with a cloth or something. But when you hover on these pixel, when you zoom this pixel and hover on it, and on my top right here, top left here, there is something called values. When you will hover on this, you will see some values around 500. So these are actually the pixel energy values, the intensities, that when the electron or some light photon strikes on the CCD cameras, it actually excite the electron, and the electron gives us these energy values. So the expected value from the bias frames were actually zero, but still we are getting these values, right? So why? So why are we getting these types of values? So do you have any answer for that? Why we are getting, any one of you guys? So why we are actually getting these type of values? So anyone can just speak out if you know. So okay, if you don't know about this, so exact value is not 0 because it's due to the instrumental cause of CCD cameras. Okay, so it is actually instrumental deflect for CCD. So we have not got the ideal CCD right now. Even if you use some other CCD, it will have some other values. So right now, let's say these pixels has around 500 to 520 values of the intensity, but maybe the other have more or less values. So however, now how we will use this bias frames to neglect the noise out of the main image. So anyone who would like to answer this question, how will we use a bias frames to get the noise out of the main image? Anyone anyone So okay, so let me tell you. So bias frames will be subtracted actually from the real images, the one I showed you earlier, and after that we will get a near to clean image. Now there will be something more kind of frames which is known as flat frames. Okay, so what are flat frames? Flat frames are actually taken in early morning or the late evening when the stars are getting set. So it gives us a homogeneous illuminance of light. So it will give us approximately a near to same pixel values in all of our frames. So when I open one of these flat files here, so and I'll just zoom out for you guys. Okay, so I'll just reopen this here. um, you see there are some stars visible, right? So when I'll just change some values from the curves, you see there are these patches which are actually in our image. So these are some instrumental defects. Okay, and there are some these pointy stars here. So these stars can be removed easily using astrometry and all that stuff, using the normalization of flats. And these now I have a very easy question for you. So while normalizing and while getting a real image after removing these flats and biases, so what do you think, like similar to our bias frames, do we need to subtract those bias frames? We subtract those bias frames from the real data, right? So what about the flat frames? So do we need to subtract the flats image of a flat frame as well, or just we need to uh, do something else? So anyone, even if you have wrong answer, you must speak out, you must interact, right? So what do you think for normalization, for those doing mathematical statistics in their daily use? How, what is the function, what is the formula for normalizing a function? So how do we normalize a function? So we will be normalizing our functions. So it is actually a array, right? So array we saw for host and nebula, those arrays actually the pixel value, single pixel value. So for this pixel the value is 4284. It's a form of numpy arrays, right? So for normalizing a function, what we have to do? Anyone? Rafal, Yashdeep, anyone? So any guesses? Subtraction or any other thing for flat frames? Okay. So let me tell you the correct one. Uh, Basically, we will be dividing this. Okay, so I'll be writing the normalization function for you guys in the cell soon. So we will be actually dividing those flat out of those to get a very clear no noise image. So you have seen those images right now. Okay, so now let's do our function. So what I will do is, first I will create a master bias. So what I will do is, I will do a median just like we do in earlier cases, right? We flatten the images, flatten the data of arrays to plot a Gaussian curve, a normal distribution. If I just show you here, I guess we did on the third day, right? Yeah, day 3. here you see for the Horsehead Nebula we have this array, so these are actually the pixel values. Then we flatten those images, and we actually created somewhere a histogram or not. So yeah, here you can see this is the histogram, right? So what is this histogram? This is actually the Gaussian curve we actually yesterday studied, right? We actually tried to model our Gaussian on the real spectrum. So yeah, so this is the same thing. So it will be actually also giving the similar thing. So we will be doing a median of these things to get a normalized value, to get a value which is less of variation. So how will we plotting doing this stuff? So we will be importing all the bias frames underscore bias underscore fits, or you can write files is equals to, we will be creating a list of all those links. So my folder is ILMT 2026 slash bias, make sure of the spellings and the syntax, bias underscore 01 dot fits. So now you see, rather writing 01 02 03 in the list, what can be the shortcut? What can be the shortcut? This is the longer method, right? So let's get out of the box. So let's use our brain. So what we have studied till now, we have studied for loops, right? We have studied for loops. So for loops in which we have studied the range. So why not to use a range that we have three files 01 02 03 and use all these 0 from range 1 to 4, import all the files. Okay, so how will we use that? Bias underscore files will be is equals to the list and f and ILMT 2026 slash bias underscore, and then what it is, 0 is same for all, right? So we will write 0 here, 0, and then curly brackets. In the curly brackets I will write I, and then up to the 2 decimals, and dot fits file. Okay, so now uh, for I in range 1 2, since we have 1 2 3 till 4. Okay, so now bias underscore files, so you see it have already printed this. So what I will do is I'll write here 01. So 01 actually gave us the value after that. So bias this is a list without writing this whole here. Okay, so because we have 14 flat images, right? So we will have to write 14 flat images. So for that we can use the same method, because we can just change this range from 1 to 15 for 14. So now let's create the code here, which is bias underscore data. Bias underscore data is also a list which contains fits dot get data. So this is also a astropy function. So basically we earlier use dot data, right, earlier. So get data is also one of the things. Let's say f for f in bias files, right? So it will actually fetch all the data in the file. So master bias, what will be the master bias? As I told you, we will do the median of all the data, so which will be is equals to np dot median. Okay, so bias underscore data and comma axis is equals to 0. So y axis is equal to 0, so that it doesn't create any index issues. So now I will make fits dot write to, I'll save the file, write to. So I will actually, while importing this to GitHub, I will not be importing this whole IMT data set, because it's 400 greater than 400 MBs. So you all already given these data on your mails, so make sure you can download from there. If it's master underscore bias and then overwrite is equals to true. so it can overwrite this fits file again if we want. Now I'll run this data. So you see I have got an error. Why? The spelling of median is wrong. So now, okay, so now it says module fits dot file has no attribute write to. Okay, so this must not occur because again our spelling are wrong. So now it's working. Okay, so now we'll calculate a mean, median and standard deviation. And now there are two methods. One, we can use numpy like np dot mean, np dot median, np dot standard deviation. But what about using something new method? AstroPy gave us the statistical package which actually use a sigma clipped stats to calculate these values for a specific index data. So let's write our different variables we need. I have written the short name for them, and I will apply sigma underscore clipped underscore stats, and then here I will write master underscore bias, and I will present it with the first index data set, like 0 index, which will be the exact data set. Okay, so now plt dot im show. So when we don't have any access data, right, we have just one data, flattened data, so we write im show. So yesterday, remember, using the flattened data set, so you see here also we use hist, because we have not used plt dot plot because we don't have any x and y axis, so we have one data set. So similarly, for one data set you can also use im show. So master underscore bias with index 0 comma the vertical minimum, so v minimum is equals to, so these are the limits, okay, will be equal to median minus 5 times std comma v max is equals to median plus standard deviation. So you can skip this step also, but just for axis and all that stuff I am just to make it decorative. So there are C maps, right, we studied in matplotlib section, right? So C map we can apply viridis or magma, any of your choice, okay, so you can keep it grayscale also. So interpolation, so say this is something new, right? There is a syntax called interpolation. So what is interpolation? Anyone? So what do you understand from interpolation? Anyone? So okay,
Interpolation is when you try to guess values between the values you know.
yes, it's actually correct. So interpolation we have defined here as none, because we don't need any custom values to be added there. Okay, so we don't need to add those values between the some other values, right? So as Rafal said, so it's a correct definition for interpolation, and it stands same for Python as well. So in the astronomical unit we don't want to add any interpolation values right now, because we don't need any random self-made interruptions, right? So we have made it none. So now plt dot show as always. So it will take some time, and I have showed you the bias graph, which is actually the master bias graph, which is a median of these three. So one of which we have already seen. So if we go here to our main page, you see master bias, and when you will open this master bias, you will be, wait a second, I don't know why by default it opens in multiple tabs. You will see that it will be actually the median value, so it will be actually the similar values, but it will be far better than the single biases, okay. So median and mean are always better than what we have from the single capture. So similarly, since we have created the master bias now, so now we will be creating the master flat. So for master flat there is something we need to know, the formula for normalizing a function. So I'll just write the same thing first. I will be importing files is equals to uh, ILMT. So I will be applying the same loop here, underscore flat underscore I underscore now I columns 0 to d. Because why 0 to d? Because it will give us the next two values, because here we have 04, 06, 07. So but after 10 after 09 it changes to 10, so we have to apply dot 02, so that it gives us both values. Earlier we have fixed value 0 because we already had 3, so we just applied 01 decimal. Okay, so now dot fits file for I in range. What will be the range? 1 to 15. Okay, so we have 14 random those flat values. So again I'll just copy the data from here, uh, this line here. Just I'll change it to flat, and here also flat files, and rest of the things will be same. Then master underscore flat will be is equals to np dot median. Same, first we will do median just like earlier, flat underscore data comma axis will remain to 0. Now something called normalization will occur here. So normalization function, which is that is f normalized. So it is a subscript, right? Okay, so f normalized is f of x and y divided by f. Okay, so it is the total value, and average will be 1 in normalization. Okay, so we will write this normalization function here. So normalized underscore master underscore flat is equals to master underscore flat minus master underscore bias. Okay, so what we are doing is we are actually getting the normalized fx values. Okay, so divided by the median or mean value of master flat minus master bias, so it will give us those values, these average kind of things. Okay, so np dot mean and then master underscore flat minus master underscore bias. Now same, we will use this last comment here, and we'll write fits right. Now just we will change the file name, which is normalized underscore master underscore flat, and now we'll press shift enter, and it has given us a big error. Why it has given us a big error here? What is the error name? So it says that file ilmt flat I is not found. So 01, it's actually inside. So okay, so I have written the path name wrong, it's ILMT 2026. Okay, so it works right now. Master flat is not defined, so there must be some spelling issue again. So yeah, I fixed that, so it worked now. So now we will be using the same method here. We will be trying to plot and see what we have already got. But just the thing is, we will replace this master value with the normalized underscore master underscore fits. What is that? Flat. Okay, so here also for the mean, median and standard deviation values, we will be doing normalized underscore master underscore flat values. So we are actually trying to do the same thing. So you see here the normalized function has more star. Okay, so it has bring up more details out of it, okay, which were not seen in the DS9 one. So after normalizing those function, we have got more details and more patches here. Now there is one thing you should remember, that this is actually a inverted image. Okay, so it is actually showing you the inverted image. The DS9 was showing you the exact image. Okay, so this is the thing. So this is actually called flat fielding. Okay, so I'll just press above here and I'll write a markdown which is not as flat fielding. Fielding. Okay, so flat fielding process. Okay, so this is the thing here. So now we will be doing, we will be uploading the science image, the real image, and now we will be subtracting the bias from it, and then after subtracting the bias we will writing a code for the flat correction. Okay, so we will be writing the code for that similarly. So now this lecture might get long because we are doing something very new. I don't think you have did this type of flat processing till now. If you have done with your astrophotography telescope or your backyard telescope, computerized one, so it will be very beneficial for you. So now cleaning.
Excuse me. Can you put the last cell, please?
Sorry, yes, Rafal.
Can you put the last cell, please?
Yeah,
I could not copy in time.
yeah.
Okay, thank you.
Okay. So it's actually the same thing, just we have added a normalize step for the flat one. Okay, because we need to divide that thing for the from the science image. So rest of the part from the bias is same. Rest of the steps are same. Okay, so cleaning the science image, which will be uh, which will be science image minus bias frames divided by flats. Okay, so this is not actually a good formula, it's just a method to tell you what we are trying to do. Okay, so I just make it a markdown. So this is not actual formula, so I just gave you ideas of what we are trying to do. So science underscore path. Science path is actually the file which contain our supernova image. So when you will even search SN 2023 IFX and you go open Wikipedia, you will see the similar image here taken on 2023 20th May. Okay, so you see these are type of details. So this is from pinwheel galaxy, right? So pinwheel galaxy can be seen from any astronomical telescope if you have even a backyard telescope, computerized one. So if you take some of the long exposure, you can get easily the pinwheel galaxy images. So yeah, it is one of the famous galaxies, right? So yeah, so similar image we just saw earlier in our DS9 software, ILMT 2026, then SN 2023 IFX. I'm just writing the name of the one fits file that we have, 01 underscore 02, that we actually opened. And then, so not dot fits, because we will be making the image data separately, so we will write fits dot get data, then science path. So you can just enter tab and it will give you some of the shortcuts to directly write. So then dot fits plus dot fits, so that it can join dot fits at the end of this. Okay, so now bias subtraction first. Bias subtraction subtraction. Now bias underscore subtracted underscore image is equals to science underscore image minus master bias. So it will be actually, it will be not subtracting some image or color bands, it will be actually subtracting the pixel values. Okay, so the array that we saw yesterday, so these values it will be going to subtract from each other. These are the pixel values. Okay, so this is the thing. So fits dot write to, first of all we are just saving a file which is just a science file which is subtracted. Bias underscore subtracted underscore image, and sorry, first we have to write the file, right? I was just trying to plot it. Okay, so path underscore, okay, so let's save it with some other name. Subtracted, name it anything though guys. Subtracted sn, okay, dot fits. Okay, now name it as bias underscore subtracted, link it with the values. What will be the values? So values will be from these subtracted. So it will be actually, so what will be the process of saving this file? So it will be first creating this file, the empty file, and after that it will be actually adding all the array values from the this variable we have defined, and overwrite is equals to true. Why true? Because first it will be creating a blank file and then it will be adding this data into it. Okay, so because we are not actually dealing with something visualized, we are actually dealing with arrays. Okay, so those numbers. Okay, so it's not like saving a supernova dot png. We are actually saving array values, we are saving those float values. Okay, we are not saving a png files. Okay, so not even we are saving a image file in the terms of fits file, but we are saving the arrays linked to that fits file. Okay, so when I'll press shift enter, so there are again I missed the spelling here, and similarly same here, subtracted, now it's correct. So I'll write the same function here again, I'll copy from here, because I'll show you the difference between both of the images now. Just I will uh, do uh, change the names here, subtracted underscore image, and here I will also write sorry, I'll write subtracted underscore image. So I think rest of the things are correct, and here in the subtracting underscore image I will assign it as 1. Why? So because earlier our data was have some other data, and now we will have some one more table which is a subtracted table. Okay, so when I'll press shift enter, you see now there is not that much cleanliness, but if you will actually try to open this fits file and compare it with the first one, there will be some pixel subtraction. So it's not that much visible because it still have some instrumental or dust patches here. So we have to remove these dust patches by division. So now we will be trying to flat those images. So I'll write hashtag 2 flatting flat correction, which will be flat underscore filled filled underscore image is equals to bias underscore subtraction divided by normalized underscore masters underscore flat fetch dot write to And now what I will be doing is I will be saving it as, what was the earlier name, divided, okay, sn underscore flat correct dot fits. Okay, so what will be the assigned value to it? It will be flat filled values with overwrite is equal to true. So you understand why we are using this kind of things, interpolation and overrides. So these are actually logical things. It's not like a proper syntax. So it's very logical. Interpolation is used because we don't want to add some random values there. Okay. So and overwrite is used because we want to add overwrite the null fits file with those new arrays. Okay. So now जस्ट अ सेकेंड गाइस ब्रो तुम्हारी कितने बजे है क्या बस ठीक है मेरी ख़त्म होने वाली है सॉरी ओके सो नाउ we'll correct this thing here std so which is again we can even copy that. I'll just write it like this here, just a second, sigma clipped underscore stats flat filled image with the index 0 and plt dot mshow flat 0. Then I'll just copy rest of the things here. Okay, and plt dot show. Now you will going to see something very good. Okay, so where is the error? Subtracted image. Okay, again I did the mistake again. So what's the error here? Subtracted. Okay, spellings sigma. Okay, so please pardon my spellings. Okay, so yeah, now you see the correction. You have the clean image of the galaxy, so it has removed all those dust passes. So this is how the image is cleaned. Okay, so there is something more, cosmic ray hits removal, so which is used by which where we use the techniques for ccd procs. So ccd procs help us to clean those noises. So when maybe the telescope is hit by cosmic rays, so how will we do that? So these are some of the very computationally aligned code. Okay, so you can also skip this for now if you want. uh, uh, that's not really very important, but in real time it's very important to also remove those things. Okay, so now what I will do is we are going to remove the cosmic rays, and we will be, however this is the very good image we got after the removal. So let's skip the cosmic removal part. However, I will be sharing the code with you, so you can see in that. So it's just few lines of code. Now, so now we'll be doing the astrometry. So for astrometry, we have to go to astrometry.net. So when you will so just a second guys, just a second. Guys, I might have to end the session here. So hello guys, I'll just end up this session here. So for the astro part, we will continue tomorrow. So I have just a very urgent work. So now for the astropy part, I just give you the overview. For the astropy, we will be astrometry. Sorry. So for astrometry, we will be using some APIs to actually use those methods of astrometry to actually get the pixel to RA and deck values. So we will continue from here tomorrow. So if you have any doubt, you can just ask me. I will end the recordings here and will share with you guys.